At a recent conference, literally down the road from me, at the Smart Grid GB annual conference, somebody said around about this time in the conference, and I'm paraphrasing here, but never have so many said the same thing in slightly different ways. So one of the challenges I face is that a lot of what I'm going to say has been covered again, which should hopefully help us keep to time. So, the importance of measurement in testing and operating of smart grids. So I guess I could stop there, because without it, we might be without power soon, and I won't stop quite there. I'll go a little bit further and explain why I believe that. That's kind of the worst case scenario, but at best, if we don't test properly and measure during the testing process, it's going to cost us a lot of money. So this is the bit that I'm not going to go into as much depth as I might have planned, as I think this has been covered adequately enough, but this is a kind of a representation of a smart grid there. So, as we've heard before, new things there are things like distributed generation, storage, not just battery, but also hydrogen, heat, potentially vehicle to grid, although there's lots of debate around that, and variable, so varying supply, if I allow slight play on words, then variable demand, which may come into play if we get electrification of heat and wider adoption of electric vehicles. So, what does this mean for the grid? As we've seen before, we had a nice hierarchical setup in the traditional energy value chain, where we had generation in the center, and then the energy flowed out, and we could roughly run the system blind without too much input. And we're moving to a much more networked arrangement, where we've got generation not just at the center. The generation is not all connected to the national grid, to the high or very high voltage networks, but we've got generation right down at the domestic 230 volt level, and as we heard in the previous session, throughout the network hierarchy. And this brings me to one of the kind of key things that this is creating, key challenges. So at the top there, we have the traditional value chain, just in a slightly different format, from generation through to the end customers. In the emerging value chain that we see, which has also been called smart grids, we have the same thing, but we have distributed generation, and a lot of that generation, as I said, a lot more with a lot more variation, which we can't control built in. And to manage this, we can either make that pipe much thicker, but even that is going to not solve all the problems of power quality and voltage control and so on, frequency control within that. And we can find expensive, often very expensive electrical engineering solutions to that. Or the alternative that's being proposed is to create this information, this digital network in parallel to the physical electricity network, which will help us control in a, dare I say, smarter way the flow of power through that network. Now this creates a number of challenges which I'm going to go through. So, going back to a previous life where I was much more involved in asset management in the aviation business. At the top left there we have a Spitfire, not a computer in sight, and it was quite happy flying along, being piloted by a pilot who had purely manual and mechanical controls over that aircraft. Modern fighter jets, like the Eurofighter, for example, are so reliant on computers to fly them, they couldn't be flown by human. Right? These little winglets at the front there need to be controlled by a computer at rates that are far quicker than we could process as a human, just to keep that thing in the air. That aircraft is now entirely dependent on a computer to maintain it and keep it in the air. So how do we move from one to the other? I mean, we clearly didn't jump from the Spitfire to the Eurofighter in one giant leap. It all started with first doing static analysis of data. The whole area of operational research was born kind of between or during the two world wars, where we looked at optimizing the use of resources, supply chains, manufacturing, missions, and so on, very much done on paper by and large. And that was the first area that we automated, but that was still very much a decision support process, maybe analogous to network planning in the topic that we're addressing today. Then this became a lot more real time. We got automated navigation systems, which provided input to people who are operating them, to pilots and so on, but still no direct control. Right to where we are today, where most of our commercial airliners fly with autopilots, can land with autopilots, and we have, right at the cutting edge, we have fighter airplanes that are fly-by-wire only and absolutely require digital processing to keep them in the air. Now, we may still be some way off with that, with our grid, and we heard this morning from Nick saying, who's going to have enough guts to actually go from IT being just an advisory and an optimization technology to actually becoming totally reliant on it for our energy supply. But I postulate that we are going to move in that direction, and it's a very slippery slope. Optimization that is kind of just making slightly better use of the resources can kind of surreptitiously just become the norm, and we can easily slide into becoming dependent on IT. Just think of GPS, for example, something that the US military invented. We started using it. Right now, if we switch that off, we'd have huge logistical problems, which the designers of that system had never envisaged. And nobody decided we're going to do that. We just kind of slid into that. So what we've got, as we're digitizing and creating this parallel digital network, we've got a huge number of sources of data. So we've got the network management systems, network management itself, the planning of assets. We heard about condition-based asset management, maintenance management, asset replacement strategies being driven by the condition of assets. We've got network operations, which is doing much more real-time interaction with the network. Potentially demand management, where we can reduce the demand based on peaks. And we've got all this data flowing into the center somewhere, or lying around in a distributed fashion, as we heard with the smart meters. And we need to somehow find a way of doing something with this. And more importantly, we need to make sure that this data is accurate. Because if we're going to be taking important decisions with this data, now, even if that is just for deep analysis and static planning, there's a huge commercial impact. But if we're using this data to actually in real time control the system, then we better be sure that this data is accurate and that the measurements are accurate, because, and that brings me to testing. So unless we test these components and ensure that each of the components is delivering accurate results, we are going to be building this on a whole system on not very solid foundations. There's that dreaded word again. So I completely agree with the previous speaker on this topic, in that it's not about the big data. It's all about the analysis. So we've got this term big data that's floating around, and you might have all heard of the V's that are being bandied about. Volume, velocity, variety, veracity, and value are the five that I've heard. I'm sure that there are more. These things tend to breed somehow. So let's look at them. So volume. So clearly, as we extend the sensors, we're going to get more volume of data. And one immediate one that comes to mind is smart metering, where we're suddenly going to have 53 million additional devices on the network in the UK by 2019, according to the SMIP program projections. Velocity. So we're generating all of this data in real time. Well, a lot of this data is being generated in real time. And there's a big question as to how we're going to look at the right data at the right time to base any sensible real-time decisions on it. Variety. We've got graphic information system data, condition data, power quality, and then the IT systems that are measuring these are now becoming more critical, so we need to measure them. So they are becoming part of the system. They're not just sitting outside monitoring the system. As and I'm using IT here, so I'm kind of including operational technology in this as well. So as the digital technology, I should say, is becoming more part of the system itself, we need to monitor and test those components to make sure that they are performing the role that they're supposed to. And I'll briefly touch on veracity. Do we trust this data that we're collecting? Where does it come from? How accurate is it? And so to what extent are we prepared to make critical decisions on that? So 2 examples. So we've been involved in the initially the Edison project in the Bornholm island off Denmark. So Edison started off mainly as an EV project, but now the EcoGrid EU is looking at smart grids more generally, specifically about wind and generating wind energy and how that interacts with consumption thereof, specifically EVs, continuing on the EV theme. And the work we're doing there is building a simulation model that simulates and predicts the flow of energy through the grid. But actually this in itself is one big test bed. Right? So that whole island, because it's got nice boundaries, in being used as a test bed both to test the individual components and measure how they perform, but also to measure at a system level, albeit a small one, but measure at the system level how the system is performing to see whether our models are actually accurate and to verify our models. And the second example I'm going to point to is much closer to home, is our smart metering program in the UK, where we are rolling out, as I said, 53 million meters to over 20,000 premises during a 5-year period. And I mean, it's not just the meters. There are communications hubs. There are in-home displays. And potentially, we can all buy consumer access devices which will integrate with this whole lot so that we can talk to our appliances in the home and send tri-signals to them and so on. All of these are delivered by different manufacturers, different organizations. This is going to be a huge integration challenge. And again, we need to be able to test all of these things both in lab and in real-life situations and measure how they work. And the other point I want to make here is that testing digital stuff, in my experience, as somebody who's kind of come from an asset management, hardware engineering part of the business and moved into software development, testing digital stuff is much more difficult. Analog stuff tends to behave in predictable ways. We can draw nice curves. Digital stuff has this habit of having states and just jumping between them and it being really difficult to determine what state it really is in and what state it will be in next. And that makes measurement and testing of these things more important than ever. So to summarize, I think IT and OT are converging. We are using much more technology that's traditionally been the reserve of the IT environment in the operating of our systems. So, and we've got a large number of these devices that are all generating data. And I think we are on the path of that data becoming more than just something that we use to optimize and inform our decisions a bit, but is actually becoming part of operating the system. It's becoming mission critical. And the devices that provide us insight into the electrical system themselves be tested and measured to ensure that they are operating as designed. And everybody will have probably seen that graph there, just an indicative graph, which shows that it's a lot cheaper finding problems early on in the life cycle. And that is even more so valid for digital equipment and software, in my experience, than it is for analog equipment that we're used to. So that's where I'm going to conclude and just say that the cost of failure here is very high. Yeah, it can be operational impact at worst. At best, we've got a high cost of repair. And we'll conclude on saying that that makes it extremely important that we test and measure early on in the life cycle, especially as we move into more digital equipment.